Okay, for this tutorial, so I would like to share you a few things because everything is actually, I think it's almost being discussed previously. So in question 6.8, okay, I modify it a little bit. So the question is just to find what is the H, the shape factor H, if the velocity profile is given like this one. So this is actually the common way to show the velocity profile. So sometimes in laminar boundary layer, so you have, for example, 2 over y over delta plus y over delta square, for example. So, but in another way to write the velocity profile is by writing u over u is equal to eta plus eta square. So sometimes people will assume that eta is equal to y over delta. So this assumption is actually based on the Blasius. If you see back my notes in chapter 4, I think. So we have the term eta is equal y per delta. So now if you have, it's depend on you. For example, if we have a velocity distribution, u over u is equal to eta of 1 over 6. So it's depend on you whether you want to solve it in terms of eta or you want to solve it by replacing eta with y per delta. So it is okay for you. For example, if you want to use u over u, it's now become y over delta to the power of 1 over 6. So it's okay. You could continue with this one. However, okay, some people don't like to use the terms of y over delta because it's contribute of per y over delta, and then the integration is become a little bit difficult. So they like to use the terms of eta because terms form that you need to integrate is quite simpler. It's quite simple compared to y over delta. So it's depend on you. Okay, however, if you want to solve problem of by using eta, you need to change your equation for delta star and also the equation for theta. So for example, normally, in previous notes, delta is equal of integration of 0 to delta 1 minus u over u and dy. So because you are changing the u over u here into eta, so you need to change u over u here into f eta, mean function of eta. Okay, so it means you change u over u here with function of eta. So you have this function of eta. So and then you need to change dy here with d eta. Okay, but you cannot just replace dy with a d eta. You must make sure that it still carries the same meaning, the same integration form. So means from here, we could say that eta is equal y per delta. And then we could write dy is equal delta d eta. Okay, delta here cannot be d delta because delta actually a fixed, is a fixed amount at certain specific point. So that's why it's become dy is equal d eta, delta d eta. Okay, so you could get this one. So and then we replace dy with delta d eta. Now it will become delta d eta. Okay, so next step, you must make sure that the limit is also correct. So you cannot use limit 0 to delta while you integrate with eta. It's totally different parameter. So you need to change the delta here. So how to change? Okay, you could see the equation here. So if y is equal to 0, so the eta is equal to 0. So if y equal to delta, so the eta will equal to 1. So means now the limit here change from 0 to delta to 0 to 1. So it's depend on you on which equation that you want to use, but make sure that you use the correct equation. So this is the equation for delta star, and this is the equation for the eta. Okay, so this is equation for the delta star. This is equation for the theta. Okay, and then the shape factor H here is the delta star over theta. So means that you need to calculate U over U equal to eta to the power of 1 over 6. So you substitute into this equation to get the delta star and to get the theta. So if you calculate, we could find that delta star is equal to 1 over 7 delta, and theta here is 3 over 28 delta. So and then the H here is 4 over 3 or 1.333. Okay, so here, so a shape factor is used in boundary layer flow to determine the nature of flow. The higher the value of H, the stronger the adverse pressure gradient. A high adverse pressure gradient can greatly reduce the Reynolds number at which transition into turbulence may occur. So if H is equal to 2.59, so the Blasius boundary layer, and it is, we could say it is a laminar flow. So if H is 1.3 to 1.4, normally it is a turbulent flow. So and then we have this situation again. So for example, for 6.14, water at 20 degrees Celsius and 1 atm flows at 6 meter per second past a smooth flat plate, 1 meter long and 60 centimeter wide. So we take Reynolds transition is 10 to the power of 6, mean 1 times 10 to the power of 6. So and then we need to calculate the trailing edge. At the trailing edge, the boundary layer thickness at trailing edge, the wall shear stress, and also the drag of one side of the plate. Okay, the calculation is same with the previous one, but you need to take attention at certain point. So first we calculate the Reynolds number. So we substitute all the value. So we get it is around 5,900,000. Okay, 5.9 or 6 times 10 by the power of 6. Okay, and then it is fully turbulent. Okay, because the limit is given here. So the limit is 10 to the power of 6. So and then it's fully turbulent. So and then we calculate the length of the laminar boundary layer. So we substitute the transition Reynolds number. So we could calculate the value of X here. So it is equal to 0.167. So and then because it is more than 10%, so it is 1/8, for example. It is 16.7% from the total length. So we make assumption that laminar boundary layer cannot be ignored. So and then we calculate what is the, I think you understand this one. We need to find what is the virtual starting point for turbulent boundary layer. So if the Reynolds transition is 10 to the power of 6, so we substitute the value here. So we use the equation for delta from the Blasius. So we could get the value of delta is 0.000835 meters. So and then we compare this boundary layer thickness. So and then with the turbulent boundary layer thickness, the delta of turbulent boundary layer. So this is the equation of the turbulent boundary layer. So we could get the value of X prime here is 0.03557. So and then we could determine the length of turbulent plate. So means that we have a plate here, we have a laminar, and also we have a turbulent here. So now we could get what is actually the length of the turbulent from its virtual starting point. Okay, so we have 1 minus 0.167, the length of the laminar, and we add with the X prime here, the virtual length here. So and then it is equal to 0.8685 C6-7 meters. So, and then we could calculate the trailing edge boundary layer thickness. So we substitute the value, this is the delta from the turbulent boundary layer. So we use Reynolds number, but we need to calculate Reynolds number for the turbulent only. We cannot use the Reynolds number for the whole plate because the turbulent boundary layer only occur at certain part. So we use the Reynolds number, the length of plate that only have turbulent boundary layer. So we get it is 0.01466 meter. And at the same time, we could calculate the shear stress at the trailing edge. So it is 47.1 Pascal. So the problem is when we want to calculate the drag force for one side of the plate, because in previous notes, I just give you this table. So we have a 3, 5, and 6 times 10 to the power of 5 with certain value, but we don't have any value for the critical number of 10 to the power of 6 here. So actually it is okay if you plot a graph from that situation, from that point. So we have this point, and this point, and then you could use Excel to get the equation there to project where the value is comes when the Reynolds number is equal to 10 by the power of 6 here. Okay, so I use this equation, I substitute that, so I will find that the value here is actually around 4,000. So it is okay for you to predict the CD for this situation, okay, as 0.073 minus 4,000 here, okay, because the number here is actually just to balance the CD, because the effect of laminar boundary layer is become smaller and smaller. So the value here, the value of 4,000 will become bigger and bigger. So if you use this value, okay, but please remember the Reynolds number here is actually the total Reynolds number that you calculate for the whole plate, not only for the distance of turbulent boundary layer. So you get a CD here is equal 0.002. We substitute in this value, substitute in the equation, so you will get it is around 27.51 newtons. So, and then we go for this one. So this is the last question for our syllabus. So water at 20 degrees Celsius, 1 atm, totally same question with the previous one. But we have a flat plate. Its flow pass through pass a rough flat plate with average roughness of 0.1 meter. So, and then 0.1 millimeters. The plate is 1 meter long and 60 centimeters wide. So please, we also take the Reynolds transition here at 10 to the power of 6. Okay, normally in real one, so when we have a Reynolds number, we have rough surface, so the transition will occur earlier. So might be at 10 to the power of 5 and so on. But at least we want to maintain the question. So let's say we have the roughness and the Reynolds transition is 10 to the power of 6, totally same with the previous question. So we need to calculate what is the trailing edge boundary layer thickness, the shear stress at the trailing edge, and the drag force. So first we calculate the Reynolds number. So we find that the Reynolds number is same, 5.9 times 10 to the power of 6. And from the question, we know that the roughness height, okay, it is can be shown as K. It is equal to 0.0001, which is 1 millimeter. Okay, this is the data that we get from the question. So, and then I hope you could refer to one chapter 6, 6.1, 6.4. It is about the turbulent flow past a rough plate. So we have equation 6.82 here. Okay, so we have the Reynolds number, mean this Reynolds number. So, and then we have equation of this one. So we have a value of Z and we have the value of K plus here. Okay, Z is actually can be calculated by K times lambda. Okay, the K here is actually the constant proposed by von Karman. So it is equal to 0.41. So it get from the curve fitting actually. So the some kind of the gradient or the from their graph. So and then lambda here, okay, it may be used as 2 over CF to the power of 1 over 2. So and then K plus here is the sand grain roughness coefficient. So this is actually the they use the previous researcher, they use the pepper sand actually. Okay, the kertas pasir, they use the sandpaper to reflect the roughness. So and then they try to they comes out with their own parameter regarding to the velocity and kinematic viscosity and so on. So they will say that K plus here is equal to K V star over nu, which is the K here is the height roughness of this one, 0.0001 meter. So and then the K plus here, K plus here is actually the relation is equal to this one. Okay, so and I'm sorry, V star is equal to U over lambda. So I just forgot to write in these notes. Okay, so by using this, okay, you have the lambda is U over V star is U over lambda. So what you need to do is what you need to do is you substitute all of this. So means we substitute this value into this Reynolds number. So and then we put Z here into this one. Okay, so means that we have 0.41 lambda. And then here we could substitute the V star here with U star over lambda. And then we could substitute the total value of this one as K plus into this calculation. So mean that now the only unknown in this parameter is actually the value of lambda. So it's quite difficult, but I think if you could use MATLAB or you could do the Excel, you could get that one quite might be 1 or 2 minutes after you set all the equation. So for to get this value of Reynolds number, so the lambda must be equal to 22.07. So when you get this one, means that you could calculate the value of V star. So we could calculate the value of V star, which is 0.272 meter per second. And then we also could calculate the value of K plus, okay, because this is the equation. And nu here is the kinematic viscosity. So please bear in mind that normally textbook will give you rho and also mu, because the relationship between these two can provide you a kinematic viscosity, nu, which is mu is equal rho and nu. Okay, that's why sometimes they will only give you dynamic and also the density. Okay, so if you calculate this, we could get the K is equal to 27.14. Okay, so this parameter is actually need to calculate the value of delta B here. Delta B means the roughness coefficient actually. Okay, so and then this is the equation. You could see the textbook actually for the about this equation. So we could get delta B is equal 5.397 meter. So and then finally we could have the value. The equation is we have lambda here, U over V star or equal of lambda is equal to 1 over K ln delta V star over nu. Again, this is the kinematic viscosity plus B and minus delta B. So here B is constant as 5.0. So this is also determined by Karman and his friend. So and delta B is come from our previous calculation. So it is equal 5.3 here. So and then if we calculate, the only unknown parameter is the value of delta, and the value of delta can be calculated as 0.03688 meters. So the boundary layer for the smooth plate for question 6.14 is 0.1466, but if the plate is rough, so the delta is increased, it's become thicker, so it's become 0.03 meters. So and then for the trailing edge shear stress, we could use this equation. So we substitute the value of V star, we substitute the value of density here, so we get it is around 73.84. And okay, so and then we also could calculate the value of the shear stress here by using the idea of this one. So lambda is equal to over CF by the power of 1 over 2. So and then we could get the CF here is equal to this one. And also the tau, I think I already explained this, is equal to CF times 1 over 2 rho U rho, okay, I'm sorry. So CF is equal to tau is equal to CF 1 over 2 rho U square. So in my previous note, might be I write this as C with small d 1 over 2 rho U square. Okay, so and then to calculate the drag of one side of the plate, so we could use the idea of this one. For example, if you read textbook, they will found that there are some correlation, acceptable correlation between the local friction and the total drag coefficient. So it is CD is equal 1.15 CF. So if we substitute the value of CF here, so we get CD is 0.00472. And then the drag force for one side can be calculated by using this equation. So we get it is around 50.9 Newton. So actually, so for the drag force here, so you may also use this equation. So CD is equal of all of this one. So and then we substitute the value. So L here is the total length of the plate, and the K here is the height of the roughness. So and then we will get half this one. So and then if we substitute the value here, so we get it is around 53 Newton. So previously we get 50 Newton, and now we get 53 Newtons. So from textbooks, okay, it's mentioned that this equation actually is a good estimation if our condition is fully rough. So fully rough can be checked by using the Reynolds number of K here. So the Reynolds number is rho U K over mu. We substitute the value of K here, and we got it is around 599. So which is it is smaller, less than 1,200. So means that our condition is actually not a fully rough condition. Okay, so if Reynolds number is greater than 1,200, yes, you could use that. However, it still give you a similar value, mean acceptable range of value of the drag force. So finally, I would like to say here, so turbulent boundary layer is actually still a complex phenomenon. So there is no single equation could solve this problem. Unlike laminar boundary layer. So in laminar boundary layer, you will find that only a few equations involved for laminar boundary layer, and you could get straightforward a very precise answer for laminar boundary layer. But for turbulent boundary layer, so it's quite complex because people are still doing research for the turbulent boundary layer.